we have discussed electric potential. What is electric potential? What was it? Just a recap. I told you, if there's an electric field, or let's say we have a charge Q1, because of this we have electric potential at some point P. If this distance is, let's say, R1, and because of P, so R1P, this is position vector, then I told you potential at P will be potential at P due to this charge Q1. This will be 1 by 4 pi epsilon 0 Q1 by R1P, and you understand direction, vector, position vector, all. I am just explaining this to you. And we have discussed the definition of potential, that the work done in bringing a unit positive charge from infinity to this point, that is electric potential. Now try to think, we have done some work in bringing this particular charge from infinity to this point. Now this charge is placed at this point. Where will this energy go? The work done in bringing this from here to here, capacity of doing work is energy. So from here to here it comes. Where will this energy go? This energy is stored at this point, which is called potential energy, electric potential energy. So you get what is potential energy. You must have studied in gravitation also, potential energy and kinetic energy. So we have electric potential at a point because of the interaction of this charge with the electric field. Which electric field? Electric field produced by this Q1. Or if we have a uniform electric field, we have some interaction of a charge when placed in an electric field. Because of that interaction, we have electric potential energy. More easy to understand is, you do work in bringing a charge from infinity to certain point in an electric field. That work is stored as potential energy. Clear? Since we are talking of charges, this is electric potential energy. Now let's dig deeper into this. Let's say, now we are not defining it, we have another charge Q2 and we have placed this charge Q2 at this point. Let this be 2, or let's start afresh. We don't have any electric field here. We bring a charge Q1 from infinity to a point, let's say P1. What is the work done? 0. Why? Because there was no electric field. Since there was no electric field, there was no force to oppose or to attract. So bringing Q1 in at a place in space where we do not have any electric field, bringing it from infinity to this point, the work done is 0. Okay, I'm putting 1 to explain that this is related to Q1. Now let's bring another charge Q2 from infinity to this point. What will be the work done here? See, we'll have to know what is the distance between these two. Let this be R12. Now we have an electric field because of Q1. So work done in bringing Q2 from infinity to this point P2 will be, we know it is Q into V. So Q into V at this point. What will be V at this point? It will be 1 by 4 pi epsilon 0 Q1 by R12. That is, you can rearrange it properly. This will be Q1 Q2 by this. So if you have to know what is the potential energy of this system, what you will do? If this is 2, so net potential energy of this system will be W1 plus W2. That is, this is 0, this is this. So we will have, because of the two charges, net potential energy is this. And you know, in a conservative field, potential energy plus kinetic energy, and if there be any other energy, then total energy is conserved, whether it is conservative or non-conservative. In conservative fields, potential energy plus kinetic energy is conserved. So what the significance of this is that if we know the potential energy, and if we know the difference in potential energy, if this system is somehow disturbed, let's say Q2 from here to here, we displace Q2 by certain amount, then we have difference in energy. That energy will go as kinetic energy. Okay, so we will use it in some examples. This is the concept. Let's say we have third point P3. I'm just extending this. So W1 in bringing this is 0, W2 in bringing Q2 is this. Now what when q3 is brought to this point. Let's say the position vectors are, this is 1 2 3, so r1 3, and this is 2 3. Okay, then what I'm writing here, w3 will be, first of all it will have to counter this q1. So from here the work done will be q1 by r13 into q3. This is the potential into q, this is work done. Again potential into q3, so here you will have 1 by 4 pi epsilon 0 q2 q3 by r23. Okay, so here because of this is this, and because of this is this. Now if you have to know the total energy of the system, total potential energy of the system, we'll just add this W1 plus W2 plus W3. So this will be this plus 1 by 4 pi epsilon 0 Q1 Q3 R1 3, and then 1 by 4 pi epsilon 0 Q2 Q3 R2 3. So this is the total potential energy of the system. Either you can learn this by heart, that in a system of charges we have this type of expression, 1 by 4 pi epsilon 0. If this is 1 2, the distance will be between 1 and 2, then 1 and 3, and then 2 and 3. If we have other charges, this will keep on adding. So either you can learn it by heart, or you can every time start from scratch. Okay, let's understand this by an example. We'll solve an example here. Okay, this is a very good example, you must understand it properly. We have an equilateral triangle with side A. Okay, the sides are A. Three charges are placed at the vertices, plus Q, and plus Q. Okay, so the first part of this question is, what is the energy of this system, potential energy possessed by this system? So this will be this. So what we can write, see, Q1, Q2, Q3 all given Q. So this will be Q square, and this is A. So 1 by 4 pi epsilon 0 Q square by A, again Q square by A, Q square by A. That is total energy of this system. We should not use W, we should use U. Actually potential energy is represented normally with this letter U. So we should have written U equal to U1 plus U2 plus U3 instead of this one. Okay, so this is 3 into 3 by 4 pi epsilon 0 Q square by A, because Q square by A and all three are same. So this will be the total energy of this system. Okay, easy, very easy. Now let this be with side A. It says, what will be the total work done in reducing the sides to A by 2? That is, we'll have another equilateral triangle, but the length of the sides will be A by 2. So obviously we'll have to apply energy. What will be that? So we know that for A, energy is this. So for A by 2, the energy will be 3 by 4 epsilon 0 Q square A by 2. Okay, that is twice of this UA. So the change in energy, that is the energy that we'll have to put in, will be UA by 2 minus UA. Clear? We have to achieve this. So this will be 2 UA into minus UA. So this will be 2 UA minus UA, that is UA. So we will have to apply this much energy to reduce the sides of the triangle to A by 2. Clear? This is the second part. The third part is very interesting. Understand it properly. It says these masses, I'm writing the energy. It says these charges have mass equal to m. Okay, so at certain time they are released. So all the three will just try to depart away. Okay, now it says at certain point t equal to t1, let's say, when the sides, the length of the sides is now 2a. Okay, so it says what will be the velocity of these particles. These are three particles with mass m and charge q, and the energy of the system was this. So the moment you release them, they'll run away, they'll depart away, because all of them have same charge. So this will run in this direction, this will run in this direction, this will run in this direction. After certain time, obviously there will be a point when, because they all have same masses and same charge, they'll depart away at the same time, that is at t equal to t1, all of them will cover the same distance. So at certain time when this equilateral triangle is with side 2a, what will be the velocity of the particle? Let's say v, all of them will be having v. What will be the velocity of the particle? So we'll use the change in energy will be converted to kinetic energy. Very simple. So what will be the change in energy? First of all, let's understand. UA is this, therefore U2A will be 3 by 4 pi epsilon 0 q square by 2a, that is UA by 2. So change in energy will be this minus this, clear? This minus this will be change in energy, that is UA by 2, UA minus UA by 2. So this is the change in energy. Where will this energy go? This potential energy, this change in potential energy will be converted into kinetic energy. And what it will be? Kinetic energy, you know, it is half mv square. Now we have 3 particles, so it will be 3 cross half mv square. This energy will be converted to this, equally distributed amongst the 3. So this will be equal to UA by 2. That is, what was UA? 3. So 3 by 4 pi epsilon 0 q square by 2a. This is our UA by 2. So V square will be V square. It will be 2 cancel, 3 cancel. So it is simply 1 by 4 pi epsilon 0 q square by m and V square. So this will be root over this. So this is the velocity of the particle when it will reach this point. And what is this point? This is the point when this equilateral triangle will be having sides equal to 2a. You have understood this? This is a very conceptual question. Okay. Okay. So let's see another example based on simple potential energy. We have a square. The length of the sides, let's say A, and we have 4 charges plus q placed at the corners plus q. Okay. Now, if you are asked what is the potential energy of the system, you know how to proceed. What you will do? Net potential energy of the system. Let's say this was blank without any electric field. When we brought this particle, so first will be 0. Okay. Then second, when we brought this, so this will be 1 by 4 pi epsilon 0, that is k, q into q square by a. Okay. Then let's say this one, where this will have energy because of this and this. What will this be? This will be root over 2a. So because of this, it will have this only, kq square by a. Because of this, it will have kq square by root 2a. Okay. And then finally, let's bring this charge. So because of this, it will be kq square by a. Then because of this, kq square by a. And because of this, kq square by root 2a. So you can add all of them. You have kq square 1, 2, 3, 4. So this will be 4 kq square by a. And then you have q square by root 2a 2 times. See, this one and this one. So it will be root 2 kq square by a, because 2 into root 2 will be root 2. So you can say 4 plus root 2 into kq square by a. So this will be the net potential energy of the system. Now, if you are asked what is the potential energy of this charge because of these charges, now I am not talking of the potential energy of the whole system. I am asking potential energy of this because of this, this and this. How we will find? Potential energy will be q into v. So let's find out what is the potential at this point because of this, this and this, and then we'll multiply it with this. What is the potential at this point? Because of this, it will be kq by a, then again kq by a, okay, this, and then kq by root 2a. So this is the potential, and we'll multiply it with q. We'll get potential energy experienced by this charge. So this will be equal to, see, this is 2 kq square, I'm taking kq square by a common. So what you will have 2 plus 1 by root 2. Okay. So this is the potential energy of this charge. Clear? Now let me give you another example. You'll be asked so many questions. I have given you 2 examples. You'll be asked so many questions based on these 2 examples. In the examination, you will have figures that charge is let's say 10 to the power minus 6 coulombs. The distance is 10 centimeters. So fine. The concept is this. You can just calculate. Now let's understand one more example concept that you will be asked in many examinations. Let's say we have a particle of mass m, okay, which is traveling at a speed of v. It has a charge q1. Now we have another particle q2 at rest here, and it cannot move. It is static here. This charge is static. Okay. Now this charge is coming. Obviously, because of kinetic energy, it will go up to certain point, from where it will return. Why? Because of repulsion. So what will be the closest point? Let's say that this is the point. This is the point till which it goes. This energy becomes 0, with this velocity becomes 0, and then returns back. So what is this distance? Let's say r. What is r? Very easy. What is the kinetic energy? Half mv square. Okay. This will be at this point equal to the potential energy experienced by this charge at this point. So the potential energy experienced by this charge at this point will be equal to half mv square, so that velocity will become 0 and then it will return back. So what is the potential energy of q1 when at this point? You know it very well. It is 1 by 4 pi epsilon 0 q1 q2 by r. This you know. So what is r? We have to find r. R will be 1 by 4 pi epsilon 0. This is twice q1 q2 by mv square. Or if radius, if this point is, if this length is given and you have to find velocity or whatever charge, so you can apply this concept to solve such questions. Clear? This is obviously they are of same polarity. Now a little twist in this example. You have understood this? Now let's say this is not static. Then what will happen? This will come to a point at which these two will start, both of them will start moving. Let's say initial velocity was u. So when it reaches this point, now it pushes this point. So both of the charged particles start moving. Obviously their speed will be same. So let's say after reaching this point, this and this, both of them start moving at v. Question is clear? We have a charge present here, q2. Another charge q1 of the same polarity comes with an initial speed of u. We know at certain point, because of repulsion, these two charges will come to a very close point from where both of them will start moving together. If initial speed was u, after they have reached that particular equilibrium point, from there they'll start moving with the same velocity. So from conservation of momentum, you know, initially the momentum was mu, this only, and after this, when both of them have started moving together, mv plus mv, this will be moving with mv and this will be moving with mv. So from here what you get? This is 2 mv. From here you get v is equal to u by 2. That is, the velocity will be half of initial velocity. Clear? Now second part, energy. What will be the initial energy of the system? Initial energy will be simply half mv square, nothing. This was moving. Now when it has come to this point from which it has started, both of them have started moving together, what will be the energy? There will be 3 types of energy. First will be the kinetic energy of this first charge, second will be kinetic energy of this charge, and third will be the potential energy of the system when the charge q1 has come in contact to q2. So this will be, first will be half mu square, was initial energy was mu square. So half mv square plus half mv square. This is the net kinetic energy of the system when they are moving with velocity v, and there will also be an electric potential energy which will be equal to, you know, 1 by 4 pi epsilon 0 q1 q2 by, if the distance is r, then it is r, 1 by 4 pi epsilon 0 q1 q2 by r. So you'll equate this, V is this, U is this, you can equate and you will get whichever variable is missing in your question. If say if U is missing or V is missing, or you have to find the charge or this distance of closest approach, whatever you can find from this. So this is the concept. Let me solve one more example, or let me give you concept of one more widely used question in examinations. We have two charges. I am giving you the concept. In your textbooks or in your preparation books, you will find so many questions like this. You should understand the concept and then you go and solve your questions. We have two fixed charges. This is Q1 and this is Q2. Okay, these are fixed charges. Let's say at certain distance, let this distance be A. Okay, so at certain distance from this charge, from A, from this charge, we have fixed another charge Q3. It is right now at rest. Now what we do, we release it. That is, initial kinetic energy of this Q3 is 0, velocity is 0. Now we release. When we release, we find that it goes in this direction. Whatever be the configuration of the charges, let's assume this goes in this direction. That is, this was stronger, so this is pushing it. What is the velocity when it reaches, let's say it is B from this? So obviously we'll have to understand what is the total length between these two. Let it be R. You get the question? We have two fixed charges, Q1 and Q2. Another charge Q3 is at rest at this point. Now we release it. That is, initial velocity was 0. It is deflected towards this charge. So it goes to this charge. What will be the velocity? Velocity at this point when it is B distant away from Q2. You can put anything B distant from 1 or 2. This is the concept. See, we know the change in kinetic energy is simply, let's say this is of mass m1, this is of mass m2, and this is of mass m3. So we know change in kinetic energy is simply half m3 v square. When it reaches this point, this is the change in kinetic energy because these two are static. What is the change in potential energy? That is the potential energy when the charge was at this point and the potential energy when the charge is at this point. So change in potential energy will be equal to this change in kinetic energy. So let's see what is the potential energy when it is at this point. Okay, so potential energy when it is at, let's say, P1 and this is P2. So potential energy when it is at P1, potential U, it will be 1 by 4 pi epsilon 0. Because of this, what it will be? Q3 into Q1 by this length, that is A, and 1 by 4 pi epsilon 0 Q3 into Q2, that is because of potential energy because of this. So what is this length? It is x r minus A. So r minus A. Okay, potential energy at P1. Now what is the potential energy when it is at P2? It will be 1 by 4 pi epsilon 0 Q3 into Q1. Because of Q1, see, this is R minus B. So it is R minus B, and then 1 by 4 pi epsilon 0 because of Q2. So this will be Q3 Q2 by B. So this is the potential energy at P1. This is the potential energy at P2. So del U, that is change in potential energy, will be UP1 minus UP2. You'll be in the question, you will be given the values of these variables. So you can find this change in energy. So you'll equate this with this del U. So you can find what is the velocity. Okay, or whichever variable is absent and you have been asked in the question, you can put these values and you can equate. Okay, I guess you are able to understand this. Now I have discussed you potential energy because of charges. If this is because of certain electric field, let's say the electric field intensity of this is E. So what will be the potential energy then? It's very simple. If you have to bring this a charge Q to this point, the potential energy is simply Q into V, and you know how to find V at this point. This dV by del V by del L is minus of this is E, electric field. So you know how to find potential, and when you know what potential is, you just multiply it with Q, that is potential energy, nothing else. So this is a simple concept, nothing more than that. We have been using it by using charges as source of electric field. One more important thing is electron volt. What is electron volt? Electron volt is the unit of energy. How? When one electron travels through a potential difference of 1 volt, it is called electron volt, 1 electron volt. What is this? 1.6 into 10 to the power minus 19 coulombs into 1 volt. So this will be 1.6 into 10 to the power minus 19 coulombs volts. Okay, so this coulomb volt is basically energy, which is joules. So this amount of joule is actually given as 1 electron volt. So 1 electron volt is this. So if you have to convert any energy into electron volt, 1 electron volt, sorry, into electron volts, you just divide it by this quantity and you will get the result in electron volt. So this is the unit of energy. When we are dealing with electron, proton, subatomic particles, this is more relevant figure.